Hello everyone, this is Xiangnan, a Ph.D. candidate of Worcester Polytechnic Institute. In this video, I will provide a brief introduction of our work. Deep convolutional neural networks have achieved high performance on computer vision tasks, such as image classification. However, the accuracy improvement is often accompanied with higher demand for computational cost. The dynamic inference is an emerging technique that aims to reduce computational cost of deep CNN during inference. The basic idea is to leverage multi-branch neural networks that apply different computational cost on input data by following different branches. Here we show a simple example of multi-branch network. The network has a main branch consists of several convolutional layers, and there is a classifier branch at each of the first convolutional layer and the last convolutional layer. When the forward propagation reaches to the end of the first branch, the model needs to decide whether to output the current predicted label and stop at here, or continue the propagation to the next branch. So how can the dynamic inference save the computational cost while keeping the accuracy? The dynamic inference is based on assumption that the difficulty of classification is different from sample to sample. The traditional CNN uses all its layers to predict every sample in the dataset. So it may achieve good accuracy, but the computational cost can be very high. So what if we use a small CNN? The computational cost can be reduced, but the accuracy can be largely sacrificed because the architecture of a small CNN is too simple to fit the hard samples. So that's why we need a multi-branch network. If the model can detect the easy samples at an early stage, we don't need to propagate the samples to deep layers. So in this way, the high accuracy and the low overall computational cost can be achieved at the meantime. But if the model cannot tell the easy samples from the hard samples, the performance of accuracy and computational cost can both be bad. So it reflects that the core problem for dynamic inference on multi-branch neural network is to find a good early exiting policy which distinguishes the easy case from hard case as early as possible. How to implement early exiting? The previous studies usually adopt rule-based policies which make use of some uncertainty measurements. In this work, we propose another option, a learnable early exiting policy. Let's still use the previous example, a two-branch network. For the rule-based early exiting policy, we show a simple example here, which is widely used in current dynamic inference models. The model takes the maximum value of the softmax probability as a measurement of the uncertainty. If the probability is higher than the predefined threshold, the model can stop here and output the prediction of the current branch. For the option 2, we propose to use a small neural network to implement the early exiting policy. In this sample, the network consists of two fully connected layers. Compared with option 1, our policy can learn from dataset. But you may ask, why do we need a learnable policy? The first reason is, the option 2 can be exactly the same with option 1 when it learns the parameters shown here. So we can see that option 1 actually is a special case of option 2, and it means a learnable policy can be at least as good as the rule-based policy if we initialize the weights and bias as shown in the figure, and it is possible to learn an even better policy from the dataset. Another important reason is the option 1. The threshold must be manually chosen by expert. Usually it requires to search on a validation site. When there are a lot of branches, the searching could be very inefficient. So this motivated us to propose a new architecture called EPNet, which consists of 2 modules, the classification branches and a set of controllers for early exiting. Then we can formulate the dynamic inference as an optimization problem defined on a multi-branch network, and the goal is to maximize the benefit score defined as a combination of accuracy and computational cost. Now we introduce the architecture of EPNet and then show how to train it. First, the EPNet has a main branch which is the same with the ordinary ResNet. On each of the convolution layers of the main branch, we connect an additional branch exit. Each branch exit outputs a predicted label and a controller signal indicating to stop at the current exit or continue the forward propagation to the next branch exit. The details of a branch exit are shown in the right side. We use a gray color to denote the layers belong to the classifier module, and use orange to denote the layers in early exiting controllers. The classification module can be trained as supervised learning, and for the early exiting controllers, it has non-differentiable component, so we must train it by reinforced rule. Our training method is slightly different than the vanilla reinforced algorithm. The gradients calculated by reinforced rule usually has high variance. It is because the default reinforced rule uses a Markov chain Monte Carlo to estimate the expected reward. But in this study, the number of possible trajectories is very small, so we can directly calculate the gradients of the expected reward. As a result, the training can be much faster than the vanilla reinforced rule. Now we briefly show some of our experimental results. We evaluated the proposed EPNet on 3 datasets. Here we only introduce one dataset that is a variant of MNIST. In this dataset, the image may have multiple digits, and the label is the maximal digit minus the minimal digit. In the easy case, there is only 1 digit, and the label is the original label of the image. It is clear that the classification difficulty should increase as the number of digits in the image increases. Here is the evidence to show the EPNet can distinguish the samples by their classification difficulty. In the left figure, we can see the easy samples are mainly outputted at the early branches, and the medium samples are mainly outputted at the deeper branches. For the hardest sample, they are outputted at the end of the whole network. As the cost sensitivity increases, all the curves are gradually pushed to the left, indicating the EPNet learns to save more computational resources. Here are the results of proposed EPNet compared with the baselines, including ResNet and other early exiting policies on all the 3 datasets. The metric is the benefit score defined previously. On each dataset, we gradually increase the beta, which represents the sensitivity to computational cost. We can see the EPNet always outperforms the baselines, especially on the variants of MNIST and fashion MNIST. The reason may be the samples in the 2 datasets have clear different levels of difficulties in the term of classification. For more details of EPNet and more experimental results, please refer to our paper. Thanks for watching.